This is Rosen, Discrete Mathematics and its Applications. We're in section 9.6 on partially ordered sets. We're going to capture a few more definitions and concepts. Here we're going to talk about the least upper bound and the greatest lower bound for a partially ordered set. And the way we encounter them is we talk about subsets of the set on which the partially ordered set is defined. And we say that an element U is an upper bound if all the elements of the subset A are earlier than or the same as U for every element in that set. And we say that U is a least upper bound if it is less than every other upper bound of A. And then we have the concept of a lower bound. A lower bound on a subset A, L is less than or equal to A for all A in the set A. And the greatest lower bound, L is the greatest lower bound if it is greater than every other lower bound of A. All right, so let's look at an example. For this Haas diagram of a partially ordered set, we're going to first look at the subset A, B, and C. We're going to find upper bounds, and we're going to find lower bounds. So I'll circle A, B, and C. And what are the upper bounds? Well, E is an upper bound. It's greater than every one of those elements. F is an upper bound. J is an upper bound. And H is an upper bound. What about lower bounds? Well, there's one lower bound. It's A is less than or equal to every element in our subset. Let's look at the next one, J and H. We'll look for upper bounds and lower bounds. There's J and there's H. The lower bounds are F, D, E, B, C, and A, but there are no upper bounds. There's no element in the set that is greater than or equal to every other element in our subset there. There's no upper bound on this subset. All right, and then let's look at the next one. A, C, D, and F. A, C, D, and F. I'm going to find upper bounds and lower bounds. Well, H is an upper bound, and J is an upper bound. There's one more, it's F itself. F is an upper bound of every element in that subset. What about lower bounds? Well, the only lower bound is going to be A. Okay, and now let's look at the example for greatest lower bound and least upper bound. Here we're looking at the set B, D, and G. I'm going to find the call it the least upper bound. What are the upper bounds for this set? Well, H is an upper bound, and G is also an upper bound. And G is less than or equal to every other upper bound. So that is the least upper bound. And for the lower bounds, B is a lower bound and A is a lower bound. But B is greater than or equal to every lower bound for this set. So B is the greatest lower bound. All right, one more definition, lattices. We say that a partially ordered set where every pair has both a least upper bound and a greatest lower bound is called a lattice. Let's look at some examples. Here I have 3 Haas diagrams for different posets, and for the left one, every pair of elements will have a least upper bound and a greatest lower bound that are the elements themselves, except if I have C and D, then the least upper bound will be E and the greatest lower bound will be B. On C, it is also a lattice because every pair of elements will have a least upper bound and a greatest lower bound. Here I've circled E and D, and its greatest lower bound is going to be A, and its least upper bound will be H. It turns out that the middle poset, number B, is not a lattice, because let's take a look at the subset B and C. This pair of elements has a greatest lower bound in A. It has 3 upper bounds, D, F, and E. But of D, F, and E, there is not a least element. So the pair of elements B and C does not have a least upper bound, so it is not a lattice. Let's look at some more examples. The set of positive integers and the divides relation. Is it a lattice? Well, every pair of elements, is there an element in the set that relates to it that is a lowest upper bound and a greatest lower bound? It turns out yes. The least common multiple will be the lowest upper bound, and the greatest common divisor of each pair will be the greatest lower bound. And since this set includes 1, it will always have a greatest common divisor, and since it is infinite in size, it will always have a least common multiple. On the other hand, here we have another set that is also on the divides relation, the set 1, 2, 3, 4, and 5. The pair 4 and 5, they don't relate in the set. They do have a greatest common divisor of 1 that's in the set, but the least common multiple of 4 and 5 is 20, and it is not in the set. So this is not a lattice. Another poset on the divides relation is a set of powers of 2 up to 16. And is it a lattice? We'll consider every pair in this set. Each pair will contain the greatest common divisor and the least common multiple of that pair. So yes, it is a poset. And then finally, what about the power set of a set, S, and the inclusion relation? If I have 2 sets, can I always create a set that is the least upper bound? Yes, I can. I can union those 2 sets together. Can I create a set that is a greatest lower bound? Yes, I can. I can take the intersection of those 2 sets, and that will give me the least upper bound and the greatest lower bound in this poset. And that is the concept of upper bounds, lower bounds, and lattices.